Okay. Okay, so let's go again. All right? Have you all gotten the software downloaded? Okay? So don't just leave it zipped. Unzip it and put it someplace so that you can actually use it. All right? So I don't know, have the Mac people got it working? Did you get it going? Okay, so here, I'm going to, okay, so for PC, I have a PC version. Okay, I take the THERM executable and I just drop it onto DOSBox. Okay, and then we see this window. Okay. So we see this, so it just gives the THERM, the version, hit return to continue. Okay? So does everybody see that? Okay. If you have a Mac and you don't, if you're sitting beside somebody, and try and get your hands on though if you can with somebody. Okay? So here's the code. So just hit return to continue. So just hit return. Okay? And here's the window that we see. So we have number 1, enter estimate species. Number 2, view the groups. Number 3, select a short menu. 4, select list file. Okay? 5, review list from format file. 6, get species from a .doc file. 7, rewrite the thermo files. And 8, run thermfit to create the NASA polynomials. Okay? So we can do lots of different things. Okay? But you guys should have, well, maybe you have some files that I had already generated. Okay? But you're starting off and you have nothing. Okay? So we want to generate thermochemistry. So number 1, enter estimate species. And the enter option default is 1. So you can either hit type 1, return, or just hit enter. Okay? So if we hit enter again, right, we now have this. So it says enter the species name. And this is the species that the name that it's going to have. Like, so remember I showed you earlier the thermo, and it was C6H5O and CH3OCH3, whatever you provide there. So you could have called it phenoxy if you wanted to, or it was called C6H5O. So whatever you're going to call the species. So I'm going to type C2H6. Let's do ethane. Yeah. Okay. So, but we're going to do ethane. Okay. So here's ethane, C2H6. Okay. So that's the name of the species. Just hit return. Okay. And now we're here. Enter the elemental formula for the species. So it takes all these different elements into account. Okay? But the elemental formula is C2H6. Okay? Now, you could, if you want to, we can try it maybe in another iteration, but you could type CH3CH3, and I think that'll still work. Okay? And we'll see later why that is. Anyway, but the number of atoms in the species, there's 2 carbon atoms, 6 hydrogen atoms, 8 atoms altogether. If this is incorrect, hit Q, otherwise hit return to continue. So okay, so enter the number of groups in the species. Okay, so for ethane, and I normally have, when I'm doing the thermo, I do all the groups and the contributions and so on, and then I prepare it, and then I use the code to calculate it. So we have ethane, C2H6. So we have CH3, CH3. So we have C bonded to C bonded to H3 twice. Okay? The symmetry number is what? For ethane. Symmetry number? 18. 3 times 3 times 2. 3 times 3 times 2 is equal to 18. And number of rotors. The rotors is to calculate the heat capacity at infinity. So how many rotors in this molecule? 1. Okay, we've 1 rotor. Okay, that calculates, helps pin Cp infinity. Okay, so we have C bonded to C bonded to H3 twice. Symmetry number is 18, rotors 1. Okay, so how many groups are in this molecule? 2. So 2 return. How many different groups are going to be entered? 1 return. Okay, how many rotors in this species? Default is 0, there's 1. Okay, enter group ID. We have C bonded to C bonded to H3 space twice. We can write it like that. We can also write, if we go back, we can write comma 2 if we want, or space 2. It's the same. I like to leave a space 2. Okay? C bonded to C bonded to H3 twice. Okay? Enter the symmetry number for the molecule, 18, return. So can everyone do that and see, do you get that menu? Everybody got to there? Okay, so the heat of formation minus 20.08, entropy 54.86, and then the heat capacity values out to 1500 Kelvin. All right? Okay, now the next part is very important. Okay, everything is very important, every step is important, but the next one. So edit these results, and the defaults are fairly obvious, and if you just hit enter, it'll give you the default. So the default is no, you don't want to edit anything, you've done everything correctly. So just hit return, and now you have this menu. Okay, and this is a very important step. So, or calculate radical based on this parent. F, add current species to an output file. Okay, H, toggle, and so on. Those first two are the main ones that you're going to use all the time. Okay, so we want to file this. We've just generated it, so we want to save it now to a file that we can use. Okay, so we type F for file. Okay, and now we want to enter output file name. Okay, and I'm just going to go Henry, maybe underscore test. Okay, I'm going to call it that. Return. And it says create a document file. Enter choice, default is yes. And choose the units. It's number 1 is kilocalories per mole, 2 kilojoules per mole, and the default option is kilocalories. So we leave it at calorie units. Okay? Enter title for the list file. If you don't enter anything, it'll take Henry underscore test. So we're going to have 2 files, a doc file and a list file with the same name. And we want to keep them the same. Okay? So that species has now been filed. Now, so enter option. And if you hit enter, you do a new species. Or if you hit R, you get a radical. So let's do the radical first. Okay, so if I type R for radical, okay, we now have this menu. And this is our BD, the BD groups. Okay, so we have a primary. Okay, you look these up yourself because I don't know exactly. Okay, but here we have primary, we have neopentyl, we have an R, which is bonded with carbon, a radical site. This J, CJ, means a radical site on this carbon, which is a secondary carbon. So this is Joe Bazzelli's code, language. Okay? J means radical site. R is any group. So it can be methyl, ethyl, propyl, butyl, isopropyl, terbutyl, anything. Okay? So for this molecule, this is a secondary. This is a primary vinylic. VIN, vinylic. ALLS, secondary allylic. Okay. C, this pound sign is triple bond C, CJ. Okay? So C triple bond C, CJ. So that would be a propargyl, but the radical from propyne. Okay? The radical form from propyne. Okay? C star C is C double bond C. C pound C is triple bond C. Okay? So just here's a C, okay, CDOJ. Okay, here we have C2H5, which is the one we're going to use for ethane. Okay, CCJC, or C dot C, is the same as CJC. I don't know why we use, but they're slightly different. This can be changed, slightly different nomenclature. But that dot is a radical site again. Okay? It's telling you where the radical site is. So you have, and you can, there's lots of BDs available. Okay? You just have a look at them. Okay? There's over 100, okay, in the file. Okay? So enter the bond increment name only. So we're going to use C2H5 for ethyl. So we type C2H5. What the difference between C2H5 and P is, I'm not sure. Okay? Have a look in the BD file and you see yourself. Okay? Enter the symmetry number of the radical. So what's the symmetry of the radical now? So the parent is 18. What's the symmetry of the radical? It's going to be 3 times 2 is 6. And do we have a twofold symmetry in the center anymore? No, because it's 2 and 3. So it's just 6, not 18. What's the radical name? C2H5. Elements, C2H5. The number of atoms is 7. Just hit return. How many rotors in the species? We still have 1 rotor. Okay, and now we get the thermochemistry of the radical. Okay, has everyone gotten that? Yeah? Okay, so we have the radical. And so do we want to edit those results? The default is no. So we hit return. And now we want to hit file again. Because we had C2H6, now we want to file our radical. So we hit file. And now the last species filed is ethyl. Okay? Now, okay, so let's do the next one up. That was ethane and ethyl. So let's do propane. Is there anyone struggling to get what I'm getting, to get the values? Or is everybody okay? Fairly straightforward. I don't want to be too slow, but I don't want to be leaving anybody behind, because I do want you to be able to use the code. Okay? So let's do propane now. Okay? So propane, C3H8. Okay? Okay, so the elements C3H8. Okay, there's the elemental composition, 11. Okay, so enter the number of groups in this species. So we have 3 heavy atoms, so there must be 3 groups. So we write 3. How many different groups are going to be entered? We're going to have 2, because we're going to have 2 C bonded to C bonded to H3s, and then 1 C bonded to C2 bonded to H2. So we're going to have 2 different groups, 2. How many rotors? There's going to be 2 rotors, okay? 1 each side of the central carbon atom. Okay, so 2 rotors. Okay, so entered group number 1. So we're going to have C bonded to H3 space twice. Okay, and then we're going to have C bonded to C2 bonded to H2. Okay. What's the symmetry number of propane? 18. Okay, so we type 18, and there we have the thermochemistry of propane. Okay, nice and handy. Okay, edit these results. No, we want to file that, type F. Okay, last species filed, C3H8. Okay, now we want to get the radicals from propane. So let's do OR. Okay, now we're given, again, the menu. What are we going to, we can take S. Let's just take P and S for the radical. Okay, so we do N-propyl radical. So it's going to be P. Is there a CJCC there anywhere? Or NC3H7? There isn't. So we do P. So primary radical, P. Okay, so enter the symmetry number of the radical. It's going to be 6, 3 times 2. Okay, enter the radical name. We have NC3H7, N-propyl radical, NC3H7. How many elements? So we see C3H7. Okay, so there's 10 atoms in it. Just hit return. How many rotors? We still have 2 rotors. And there's the thermochemistry of N-propyl radical generated. Do we want to edit those results? No, but we want to file. Okay, and now the last species filed is NC3H7. Okay, now if you're with me to here, this is a critical juncture, right? It's something new again. Okay, so let's do OR now. We want to do isopropyl radical. So we've done N-propyl, but we want isopropyl, right? So we do OR again. Okay, so now we have this menu. It's quite clever. It says, calculate the dry radical from the last radical, or calculate a different radical from the parent. Okay, so we want a different radical from the parent, so we choose option 2. Okay, and now we just do S, secondary this time. So we had primary, now we're doing the secondary one, S. So enter the symmetry number of the radical. This now is going to be 3 times 3 is 9. But it's not, I don't think it's 18 because the hydrogen atom is there. So it's actually 9, not 18. So the symmetry number is 9. The radical name, we call it IC3H7 for isopropyl radical, as opposed to N. Okay, IC3H7. And then C3H7, the number of atoms. How many rotors? We still have 2 rotors. And there's the thermochemistry of isopropyl. We hit return and hit file and save it. Okay? Everybody with me? Okay? Say, okay. Okay, so now X exit program or Q return to the main menu. So let's go Q at this stage. Okay, now we have this menu. We're back to the main menu again. But now we're done. So we've ethane and ethyl. We've got propane, and we've N-propyl and isopropyl radical. So now we want to generate the NASA polynomials so that we can have those for Chemkin or Cantera or whatever code we're going to be using. Okay? So we want to get run thermfit to get the DAT file. So we type 8. Okay? And now it says enter the file name, and I called it Henry_test. Okay? Enter the DAT output file, and we want to call it Henry_test. Keep everything the same. Okay? And now it's generated. So if I now can exit the program. If I just type X, it's going to exit that, and I shut that down. And I go back here to the THERM directory. And in the THERM directory now, I have 3 files. Okay, unfortunately, it's limited to 5, is it 8 characters long or whatever? Okay, so it's Henry_te is .dat.doc.lst. Okay? And this is a bit unfortunate because you're also limited in number of characters for species names. Okay? So you have to be careful in giving species names that you don't use a species name that's too long. Otherwise, you can get duplicate species names. Okay? So just be careful with that. But if we just look at the .dat file, there it is. Okay? Here's the term. Okay? It's very similar now to what I showed you earlier. Okay? Here it is, ethane. It was generated today using THERM. There's 2 carbon atoms, 6 hydrogen atoms, no oxygen atom, no nitrogen atom. In the gas phase, the low temperature ranges from 300 to 1383. The cutoff is 1383, and then the high temperature range is 1383 to 5000. So these first 7, 1, 2, 3, 4, 5, 6, 7, will give you the thermo. In the high temperature range, the next 7, 1, 2, 3, 4, 5, 6, 7, will give you the thermo in the low temperature range. Okay? And with the whole range, you get from 300 to 5,000. Okay? So there's ethane, there's ethyl, there's propane, N-propyl, isopropyl. Okay? All calculated for you in the format that's necessary for the codes. Okay? Very nice. Okay? So that's a file using group additivity. Here's the .lst file, okay? And here's the information.lst file, which is nice. It gives you the tabulated values of the thermo. So, you know, you have the NASA polynomials, that's fine, but they're weird numbers that don't actually give you the actual values for the heats of formation and so on. So check these. Typically, I'd go to NIST database. Check in the NIST database, how is your THERM compared to what's in the NIST database? Is it calculating reliable values or not? Okay, get some sense of where you are. Okay, just double check everything. And then the .doc file, it thinks it's a Word document, but I think this is actually generated before Word was ever released. Okay, so be very careful and don't edit these files because they have to be either 70 characters long or 80 characters long. And if they're 79 or 81 or whatever it is, the code goes belly up, right? So don't mess with the file or it won't work. Because what you want to do is, you want to be able, so I worked in Lawrence Livermore Labs from 94 to 99. I still have THERM files that I generated when I was there, right? 20 years ago. I can now take those, upgrade my group values, and upgrade all my thermochemistry with a press of the button, right? If they're corrupted, I'm hooshed, right? So I have to be very careful not to corrupt them. Now, there's a way you can actually fix it, okay? And I'm not going to go into that, but you can actually fix them, okay, and make them the right character length. But best not to mess with them, okay? Because it does it'll open in Word, and it's fine. You can look at it in Word, but just don't edit it, right? But what I want to show you here is, look, the doc file gives you all the information, right? So here you have, here's the group, C bond to C bond to H3. You have 2 of them. Here's the heat of formation, entropy, and heat capacity values. There's CP infinity. Here's the number of rotors. That's the symmetry, and that's the creation date, okay? And if you go, then you scroll down to ethyl. It says thermo estimation for the radical. Gives you the radical name. The radical is based on the parent, which was C2H6, which is above. And it gives you the group values. And here's the BD group that you used. Okay? So, and then here's the thermo. Then there's propane. And then here's N-propyl. And now it's saying the radical is based on the parent C3H8. Okay? And all of this was saved when we were doing the saving. And remember when you had this window, you wanted a diradical or a second radical based on the parent. So we did isopropyl, and we said a second radical based on the parent. So it took the parent, which was C3H8. Okay? And just to prove that it did, there it is. And these are the groups from the parent, and then that's the BD value for the radical. Okay? And now there's all your species. You're done. You can keep those forever. You can use them to update. If you update your group value, your S changes, or the group values for C bonded to C bonded to C, H3 changes or whatever. You can rerun this again. It'll take it, and it'll say, do you want to update the value? Say yes. And then it'll give you updated. So once you've generated it once, it's precious. You can keep it and update the values again. Okay, so let's go back a little bit now. So we've done those three species. And just for, okay, so now we want to do a few more. Okay, so we're going to estimate species again. So what one will we do this time? Let's do isooctane, because that was quite complicated. So isooctane, IC8H18. Okay, so enter the formulae here. So it's C8H18. Okay, so 26 heavy atoms. Right, enter the number of groups in the species. Now, I'm going to have to go over here to remember. We had C bonded to C bonded to H3 5 times. C bonded to C4. We had C bonded to C2 bonded to H2. And we had C bonded to C3 bonded to H. Okay? But we also had gauche 3. We had 1,5H repel 1. The symmetry number was 729. And now what's the rotors? How many rotors do we have in isooctane? One, two, three, 5, 6, 7, 8. So we have 1, 2, 3, 4, 5, 6, 7. So 7 rotors. 1, 2, 3, 4, 5, 6, 7. 7 rotors. Okay? So we have 5, 6, 7, 8, 11, 12 groups. So we have to enter 12 groups. Okay, so enter the number of groups for the species, 12. How many different groups are going to be entered? 2, 4, 6. How many rotors in this species? 7. Enter group number 1, C bonded to C bonded to H3 5 times. C bonded to C4. C bonded to C2 bonded to H2. C bonded to C3 bonded to H. And it doesn't matter in which order you enter them. Okay, by the way. It's gauche, GAUCHE, 3 times. Okay, so it wasn't happy with that. I forgot the G 3 times. Okay, and group number 6, we have okay, I hope I remember this now. Oh, it's not, it doesn't like that. Uh-oh. Okay, I'll have to come out and look. Okay, so here it's H/repel/15. Okay, so here they are, and actually we've changed the gauge here. It's no longer 0.7, it's 0.8. Okay, so it's changed slightly. Okay, but here this is called H/repel/15. Okay, so that's what it's looking for. So I'll put it in here. H/. Okay, so okay, symmetry number 729. Okay, and there we have isooctane. Okay, so we don't want to edit those results, but now we want to file them. Okay, file. Okay, and now we want to enter the output file name. So I want it to go into Henry's_test again. Okay, so create the document. So we want to say yes, we want to create it. But now it says, the document already exists. So what do you want to do? Do you want to overwrite it? Or do you want to add to it? And we don't want to overwrite it. We've already done a lot of work in generating the other species. Okay, so be careful, right? We want to append. So option 2. Okay, and it'll also save to not only the list file, but the doc file. So we want to append to that too. So type 2 for that as well. Okay, and now if we do another species or a radical, it's going to keep adding to that same file. Okay, so we've picked up where we left off. So we can go have a lunch, come back, and continue generating our thermo into the same file. No problem. Okay, so now let's do a radical, I don't know, just for pig iron, and now this time we can do primary, okay? And then what's the radical name? It's AC8H17. Sorry. Okay, I've messed up. Okay, but we can go back and fix it. Okay, so it asked me for the symmetry number and I gave it its name. Okay, so it's going to assume 0 or 1 for the symmetry, 1. Okay, so that's wrong. But radical name AC8H17. That's okay. We can correct it in a little while. Okay, so C8H17. Okay, there's the number of atoms. How many rotors? There's still 7. Okay, now there's the radical. But do you want to edit these results? So if we look in here, the symmetry number used to correct the entropy value is 1. Because I put in the name of the molecule when I was looking for the symmetry number. So I messed up. So do I want to edit those results? Yes. Look at the symmetry. The entropy is 116.36. Okay? That's wrong because the wrong symmetry number is used. So we want to edit those results, so we hit yes. So what are our options? Okay? So 1, change the symmetry number. Okay? Common mistake, obviously. So it's option 1. Okay? So number 1, I want to change the symmetry number. Okay? 1. So what is the symmetry number of the radical? So I don't know. I can't think. So it's 9 times 9. It's 81 times 2. It's 162. So it drops from 729 to 162. Okay? Okay, so it's 162. Okay, and now our entropy drops by 10 units. Okay, it was 116, whatever it was, now it's 106. Okay, that's a big difference, okay, in your equilibrium. All right, so, and now we don't want to edit those results anymore. We have it corrected now, so we want to file that. So that'll go into our thing. Okay, so now we can do another radical. Maybe I'm getting boring, I don't know. or calculate as a different radical from the parent. I'll do 2. And now we want to do S, secondary. Okay, enter the symmetry number of this radical. So if we have a radical site here, what's the symmetry number of the molecule? It's still 729. Okay? So we give it 729, it's the symmetry number. Enter the radical name, BC8H17. How many C8H17? Okay, and how many rotors? Still 7. Okay, and there's the thermochemistry of the secondary radical. Okay, we file that. Okay, and now we're generating not only the parent, but all the different radicals. We can do the third one. Let's do the third one, F. Okay, so sorry, R I should say. Okay, calculate different radical from the parent, 2 again. Okay, and now we do T, tertiary. Okay, and what's the symmetry number of this radical now? Is it 81 times 9? So, but does it go up by a factor of 2 or not? Okay, so does everyone know what I'm asking? Okay, we have a radical site here now. Okay, so what's the symmetry number of this? So it's going to be 3 times 3 times 3, 27, times 3 is 81, and then we have 3 times 3 is 9, so 81 times 9. But is there a two-fold symmetry here or not? Yes. That was pretty categorical. Okay, so 729 times 2. Okay, so what's that? 1458. So 1458. Radical name C8H17. C8H17. And rotors 7. Okay, and now our entropy is 104.52. Okay, and edit these results, no, and we file it. Okay, and there we have A, B, C. We can do D. We can do the last one as well. Okay, so that we have all our radical species. Why don't we do some oxygen, maybe oxygenated, like methanol? We do methanol. Okay, so enter the species name CH3OH. Enter the formula here, CH3OH. Okay. Okay. So enter the number of groups in the species. We've got 2 heavy atoms, so we're going to have 2 groups. Okay, so we have 2. How many different groups are going to be entered? 2. So how many rotors? We have 1. Okay, now enter the group number 1. So we've C bonded to H3 bonded to O. Okay, so remember it's an alphabetical order. Okay, so it's not C bonded to O bonded to H3, like C bonded to H3. C bonded to H3 bonded to O. Okay, and then O bonded to C bonded to H. Okay, enter the symmetry number of the molecule, it's 3, and there's methanol. Thermochemistry for methanol generated. I did these results, no, we file it. Okay? Now we want the radical, or. Now, so this one, now, if you look here, it's actually down here, CJOH. Remember I said J is radical. So CJOH is CH2OH. Okay? So we want to choose number 22H, which is CJOH. And you give it its name, not its number. CJOH. Hit return. So enter the symmetry number of the radical, it's 2. Enter the radical name, CH2OH. How many elements? Now watch this time, CH2OH. I don't bother saying, well, hang on, no, CH3O, right? You can just type CH2OH, and then it picks it up, okay? No need to write, okay? And then you hit return. How many rotors? There's 1. Okay? And now we have hydroxymethylene radical. Okay? There it is. Okay? Edit these results. No, we want to file it. Now we want to do another radical, and we want to do a radical based on the parent, so 2. Okay? And now this time we want the alkoxy, CH3O radical. So it's alkoxy. So if you just type ALKOXY, alkoxy, okay? There. Now I'm after inadvertently hitting return twice on that. Okay, so symmetry is going to be 1, so I'll have to correct that in a minute. Okay, so enter the radical name, CH3O. Okay, CH3O. There's the elements. How many rotors? Now, this time, do we have a rotor on the CH3O? Is that a rotor? No. Okay, so there is no rotor. It's 0. So the default is 0. Okay, so I just explained that. Okay, so we have CH3O, and then the H. Remember, these molecules are not linear. There's angles for the bonds, right? So when you're rotating here, there's a moment of inertia that is felt around that bond, okay? So that moment of inertia then adds to the thermochemistry, okay? When we remove the hydrogen atom here, now this is like a top, and there's no rotor there anymore because there's no moment of inertia in it, okay? So you lose that rotor and 0. Okay, so the default is 0, so you can just hit return. Okay, now you see here the symmetry number for the entropy correction. I inadvertently had hit return. Okay, so we have to edit those results, change the symmetry number to 3. Okay, and now it's corrected. Okay, no big deal. Hit return and file. Now, there's another time when you lose a rotor. So let me just do propene. Let's calculate propene. Okay? So we're going to enter new species. So we just hit return. So we have C3H6, propene. So C3H6. Okay. So how many groups? I better draw it. So we have C bonded to double bond C, C. Okay, so we have H2, H, H3. So we have CD bonded to H2. We've CD bonded to C bonded to H, and we've C bonded to CD bonded to H3. Symmetry is 3, and rotors 1. Okay? So how many different groups? 3. How many different groups to be entered? 3. How many rotors? We have 1. Okay? We have CD bonded to H2, CD bonded to C bonded to H, and C bonded to CD bonded to H3. Symmetry number is 3. Okay? And there's propene. Okay? So we edit those results. No, we hit file. Okay? Now we have R. Okay? Now we want an allyl. If we abstract the most easily abstractable hydrogen atom is from the methyl group, and we have an allyl radical. Okay? But it's a primary allylic, so it's allyl P. You could have, so say for instance, you had CH2, CH3 in one butene. Now you can still abstract this hydrogen atom, but that be secondary allylic. Or if you had this molecule, you can abstract this hydrogen atom, and it's tertiary allylic, allyl T. Okay? So you can have allyl P, allyl S, allyl T. Okay? Depending on the hydrogen atom. Okay? So in propene, it's allyl P. Okay? So enter the symmetry number of the radical. Now, what's the symmetry number of the radical? For propene. Oh, I have it all messed up there now, sorry. Okay, so we abstract that. We have this. Okay, and actually, what is the situation we have? We have a resonance delocalization. So the symmetry is actually 2. Because if you're standing across this bond, you look left or the right, it's 2. So the symmetry is 2. Okay? Enter the radical name, C, or, well, A, C3H5A, C3H5A, backspace minus A. Okay? C3H5. How many rotors? Now, this is another reason that I did this molecule. How many rotors do we have here? 1, 2, or none? None. None. Okay? Because a double bond, you don't have a rotor. There's no rotation. Okay? And you have a bond and a half either side. So a bond, anything above a bond, no rotor. So once you have the half a bond, you lose the rotor. So you have no rotor at all in allyl. Okay? So it's 0. Okay? So the number of rotors there is 0. So that's the default. So we hit return. And there's our thermo for allyl. Okay? We file that. Sorry. File. And there's allyl. Okay? Now we can do the other species as well. So we do R. Okay? A different radical. Okay? And now we want to do, let's say we want to do this radical here. We put this back, and we take one of these. Okay. Okay? So we've taken away this, the vinylic hydrogen atom. But what type of vinylic hydrogen atom is this? It's primary. Okay? So remember I said you have Vin and Vin-S. Okay? So that first one, the terminal one, is Vin. So we type Vin. vinylic. Okay? So what's the symmetry number of this radical now? It's still 3. What's the radical name? I think it's C3H5 minus S. And it's C3H5. Actually, this naming minus A, S, and T originated actually with Philippe Daguet, who actually originally gave them those names. Okay? How many rotors? We have 1. Okay? Because we now have that methyl rotor. Okay? So it's 1. Okay? And there's the thermo of that species. And we hit file. Okay? And now we go R again, 2, and now we have Vin S. Okay? Enter the symmetry number of the radical. It's 3. Enter the radical name, C3H5 minus T. 4 elements, C3H5. How many rotors? We have 1. Okay? And there's the thermochemistry of that radical. Okay? We hit file. Okay? And now I'll exit. Okay? Is there anyone formaldehyde, or should I do acetaldehyde? I showed you earlier what that one, or a ketone, acetone. What if we do acetone? Okay, we can go again. Okay, so if you do acetone, so it's CH3CO, CH3. CH3, CO, CH3. Okay, how many different groups? 1, 2, 3. So enter the number of groups in the species. There's 3. How many different groups? 2. How many rotors? 2. So we have C bonded to CO bonded to H3 twice. And CO bonded to C2. Okay? And the symmetry number is 18. If you're sitting on the CO, you look left or right, it's the same. So it's 3 times 3 times 2. Okay? It's 18. So edit these results. I just want to check one. Enter the new symmetry is 18 as well. So it's not changed. Okay? So I had it at 18. Is that all right? And that's acetone. Okay. I think that's probably edit these results. No, we file it. Okay. So now we can Henry underscore test, append, and append. Okay. And now what we can do is we can hit quit, I think. And now we can run 8. We get our Henry dot test and Henry dot test. Okay, and now let's just see what it's done this time. Oh, okay, I typed the wrong thing. I was too... Okay, but I can just rename this as Henry.test. There's no problem. Okay, but they're all my species now. Okay, and I've saved them all into the file. I haven't lost anything, and now I have the .dat file, the thermo that I can use in my code for everything. Okay, so this is just a tool for you guys to use to generate thermochemistry of species where you won't have it available to you. Okay, but if you use group additivity correctly, you should get an accurate estimate for the thermochemistry of the species, or reasonably accurate. estimate for the thermochemistry of the species. And it's something to use. You know, so, and of course, it depends on you realizing isooctane has 3 gauche, 1,15, and this kind of thing. You know, that those have to be taken into account to get the most accurate values out of it. Okay? So it's only as good as the user and what you put in. And also the values that are in there, okay, in terms of accuracy. And we're, as I said, we're constantly updating this, trying to get more and more accurate values. Right? I think that's probably a good place for us to finish today. I know we're finishing a little bit earlier than the full time, but it's pretty much the 3 hours up. And I hope that was a good introduction. I like to spend an hour going through THERM, just using it. Okay, so it's a play with it. Have a look at the files. See how the BD is used to generate the thermo and so on. Do it by hand yourself, just to see how everything works. All right? Thank you very much.